Yesterday we did horizontal asymptotes. As I said, I've said this before, you can have either a horizontal or an oblique and not both. And we did the horizontal asymptotes and the testing of horizontal asymptotes. And today we're looking at oblique asymptotes. And we're going to do two questions. One, we're not going to sketch. We're just going to look at how to find the oblique asymptote and how to test around it. And then we're going to do a sketch. And the testing is different. It sort of starts out the same, but the conclusion is different. So again, you really do have to have a good sense of the vertical, the horizontal, and the oblique, and all three types of testing. Okay, and again, a reminder, remember this, oblique asymptotes occur in rational functions when the degree of the numerator is exactly one more than the degree of the denominator. If it's more than one more, something else happens that we don't look at in this course. Okay, if you're thinking about this, especially when we get to how to calculate them and you wonder about it, I bet you could guess, give a good guess as to what would happen if you had like 4 on top and 2 on bottom or something like that. But ours will always be a difference of 1. And you know what happens if they're equal? If the degrees are equal, you have a horizontal asymptote and it's not 0. And if the top has a lower degree, then you have a horizontal asymptote that is 0. Okay? But oblique asymptotes occur in rational functions when the degree of the numerator is exactly 1 more than the degree of the denominator. So let's start with this question here. Determine the equation of the oblique asymptote and the behaviors around it. That's all we're doing, not doing a sketch for this one, although we will probably sketch the asymptote just to briefly talk about it. Again, normally, we often notice that there's an oblique asymptote versus a horizontal asymptote. That might be one of the first things you look for, just generally observing what the degree is on top. So on top, it's degree 2, right? And on bottom, it's degree 1. So as we just talked about, we have an oblique asymptote. Oh, thank you. Right? We have an oblique asymptote here versus a horizontal asymptote. So you might do that first, and then generally we would factor both the top and the bottom. Just to get that out of the way. Then we do intercepts. Then we'd find the asymptotes and do the testing around the asymptotes. And at that time, we would have all the information we need to start sketching. That's how we'll do the oblique as well. But we're going to skip intercepts because we don't have to because we're not sketching. So step number 1, I'm not really doing formal steps here, but if you want to think about it this way, you can. Step 1 is we're going to divide. What are the 2 ways that we learned how to divide?
I was going to say like elimination. It's like if one of the terms cancels out, you're allowed to. Oh wait, no,
that's not what I'm asking, but you're right. Synthetic and long?
Yeah.
That's okay. And remember on the test, a couple of tests ago now, where there was a question that said, find the remainder without dividing, and there's a whole bunch of people who were like, ooh, I'll be slick and I'll use synthetic. I was like, oh no, that's still dividing. Synthetic is a type of division, unfortunately, right? That was a remainder theorem question. I think we talked about that afterwards. Anyway, so you can use synthetic or long. Most people like synthetic when you can. In these questions, sometimes you will not be able to use synthetic and you'll have to use long division. Okay, so remember the cases when we can do that. So let's go ahead and do that. And, well, what are we dividing? This is a fraction. If it was 3 over 2, we think of it as a fraction of 3 over 2, but it also means 3 divided by 2. This is a rational function, but it also means that divided by that. That's what makes it a rational function. So that's the division that we're actually doing. And in this case, we certainly can use synthetic. So it's x plus 2. And then, yes?
Should you try to factor it first and see if stuff cancels out?
Yes. No, if there's a hole, that's going to change the situation very much. So I think it's a good idea to always factor first. this question's not set up for that 'cause it's not a sketch. But yeah, like I said, I think it's a really good idea to always factor first, or if you're given factored form, I think it's a good idea to expand it, just because sometimes you want one form for something and the other form for something else. So I think that's always a good idea. So we'll do this quickly. And we didn't get a remainder of 0. What do you think about that?
Can we just turn it into a perfect square and have like the plus on the end?
Well, that makes sense, what you're saying, yes. What do you think about this? What does it mean if it's not 0?
It's a good one. I guess it would be like that 9% or something.
Not necessarily. It's not a factor. But doesn't that make sense? What would it mean to be a factor? What would it mean if x plus 2 was a factor of that? It would be a whole, which is like what you were just saying. So there's no surprise that there's a remainder. There should be a remainder. Usually there is a remainder. Okay, and then you might think step 2. Now we're going to do it a little bit differently here. I'm going to write things out a few extra steps, and then on the next, which you're welcome to do if you like, but on the next, when we do the actual sketch, I'll show you how you can kind of shorten things. So step 2 is write out your division statement. And I'm just going to remind you of what this means. What we've done with doing the division means that this, which is 3x squared plus, is that right? Yeah, plus 2x minus 4, which was just the numerator, is equal to what? X plus 2, the dividend, and then the quotient, which is 3x minus 4, plus the remainder. Do you remember doing that? It's quite a while ago now, but division statement. But f at x is 3x squared plus 2x minus 4 over x plus 2. Right? So if I want this to be the function, which is what we want, I also write it over x plus 2. I'm just going to summarize again quickly. If you understand this, it's better. If you don't, it's not the end of the world. You can still do this. Although I hesitate to say that because understanding is always important. If this equals this, when I divide the left side by x plus 2, I would have to divide the right side by x plus 2, right? That's clear. That's obvious. And the left side now is our function, our original function. So this must also be our function. Don't you agree? We've just rewritten it. Why in the world would we rewrite it? Well, you'll see in a minute. So this is actually what you'll usually have to write. Therefore, f at x equals and what do you see about this? What do you notice? Now, when you're adding on top, not quite, but sort of. What if can't we rewrite it like this? Yeah? And now, Seema, you're right. Okay. So this is kind of a big deal. This is kind of interesting. We rewrote this function, which was our original function. We know we know sort of what that's going to look like. It's going to have all those weird curves of the stuff we've been sketching over the last little while. So that's a pretty complex function. You agree? Yeah. We rewrote it this way, and then we rewrote that and saw that something canceled. Now, by the way, we set it up to do this, right? Like we divided by x plus 2. So the x plus 2 is always going to be there. It's always going to cancel. That's the whole point, exactly. But look at this. So what is this?
Looks like a line.
It does look like a line, doesn't it? But what is it actually?
But didn't we do something where it's like the parabola and then like it will turn into a different line like halfway through?
Yeah, it's not like that, but that's an interesting idea. Piecewise function is what you're talking about.
Is it absolutely
Well, yeah, I think I know where you're going with this. You're a bit ahead of us on it, though. What is it just in general? Like we said, f at x equals this, equals this, equals this. So what is that? Huh? It's f. It's our function. That's the same function. That equation, which looks like a line, is the same function as that. Isn't that strange? Isn't that hard to believe? No, Max, you're cool with that? You believe it?
Well, yeah, because like 3x squared would be a parabola, and like because the degree 2 on the top and degree 1 on the bottom, 2 divided by 1 are being like if you take out one of the x.
Yeah, I see what you're saying.
So like it's a line. So it does make sense.
Nice, interesting. But how do you get all this stuff happening in the middle? No, were you going to say something?
Well, if those two equal, then why do you do that?
So there's something else that's interesting, and it
Why do you not in general?
yeah. I'm gonna answer your question, and this comes back to what Vang was saying. What happens when x gets really, really big? To this part, just that part right there. What happens when x gets really, 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 really big? Huh? This part gets small, right? So if this is like a million, so 1,000,002, 4 over 1,000,002 is really small. So when x gets really, 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 really big, this is basically 0. What does this graph look like? It looks like that. It looks like this. When x gets really, really big, this part is basically 0. So this is basically your function. What happens when this is really big but negative? I'm going the other way on the graph now. So I'm like negative, x is negative 1,000,000. Again, this is basically gone. This is basically 0. And my graph basically looks like that. So what is my oblique asymptote? Like what is it?
Just the part on the left.
3x minus 4 is the oblique asymptote. So when we were trying to find the equation of our oblique asymptote, we found it because we found this part that becomes negligible as x gets really, 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 really big to the right or really, 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 really big to the left. This is gone, and that's all that's left.
I would assume like how it's really small, like it's an asymptote.
It's really small because it's got a big number in the denominator. When I take the reciprocal of a big number, what do I get? A small number.
Like I don't get like what if you're
But if we want it to be the asymptote, you're right, we don't have to make x a big number. We can make x anything. But if x is small, then I'm in the middle of the graph when the asymptotes aren't occurring there. Are you still unsatisfied? By what?
I just don't understand like why I don't get what's happening.
Okay, well, I'll explain it one more time, but maybe bear with me, and when we do an example, it might make more sense. We're going to do the testing as well, and that might help also. So, but we talked about this before. 1,000,000 is a big number. What's 1 over 1,000,000? Small number. Almost 0, right? So when x is really big, like 1,000,000, this part won't matter. So it's going to be 3,000,000 minus 4 plus almost nothing. So basically, when I get out to big x values, my graph is going to just look like that. Or big x negative values, my graph will just look like that. In the middle of the graph, it's going to do other things. And we already know how to find those things with looking at intercepts and vertical asymptotes. Okay, so we got to do our testing. Oh, so the last part is now that we know that our oblique asymptote is y equals 3x minus 4.
Why is it an asymptote?
Because it's going to approach, but never touch it. Think about this. As x's get bigger, this continues to get smaller, but it's never 0. So this is the difference from that, because you're taking that and you're adding this. So you're adding less and less and less and less every time x grows. So you're getting closer and closer and closer to it.
What happened if x was -2?
What would happen if x was -2? What is it? You tell me. Look at the original function. What happens when somebody tell me what happens when x is -2? Vertical asymptote. So it's still in this form of the function, which makes sense that it wouldn't divide out. Okay, so we have a slope of 3 and a y-intercept of -4. You're going to need that, and you're going to need. Remember when I told you how you have to know how to graph lines? If you don't graph your asymptote properly, it's going to be really hard to draw the graph properly. And then, our remainder, r at x equals this, 4 over x plus 2. And that's what we're going to use for our testing of the behavior. The part of this that's similar to horizontal asymptotes is that I'm still going to check negative 1,000 or 100, whoops, and positive 100 or 1,000. So, so yeah, I am going to check those two. I need a little bit of extra space though. I'm going to check those two, but the result of them is going to be different from horizontal asymptotes. Our interpretation is different. And again, I think often for this, not always, but often, you don't have to actually use your calculator. 4 over 1,000 plus 2, negative 1,000 plus 2, is 4 over negative 998. Is that number positive or negative? So it's negative, and it's really small, isn't it? So what am I doing? I'm basically on my asymptote, except I'm subtracting a little bit. So where am I relative to my asymptote?
You're on the left side.
Well, it doesn't have a left or right, does it? It's slanted. Below, because I'm on that line subtracting a tiny bit. Use the remainder to figure this all out. So when we do the division and we break it up into the oblique asymptote, we need that for graphing, but the remainder we need for testing. And you don't need to show all this work every time. You'll see when we do it. But this is obviously a positive number. So where am I? Above. So that's how you do the testing. All I'm going to do to show you what this means is very quickly graph our line. It was 3x minus 4. So how do you graph that? You go to -4, and you go up 3 over 1, up 3 over 1, up 3 over 1, something like that. Okay? And as I'm approaching, as x's are getting really, really small, so I'm going to the left, I'm approaching from below. And as x's are going to the right, I'm approaching from above. So I can locate where my graph is. And along with all the other stuff that we've done, it'll make sense as to what it looks like.
Are you allowed to cross?
Yeah.
Oblique?
Because think about it. When x values are just around 0, like what's going to happen between these two things? I don't know. You're just going to get some numbers and add them together. Anything could happen. It's only when this part goes to 0 that it looks like that. Otherwise, this has a big impact on what this looks like.
So the 3x minus 4 is the oblique asymptote.
That's right. That's the equation of the asymptote. Because that's when this goes to 0, that's what this graph will look like. So it makes sense from that perspective. But it's interesting to me that that equation is the same as the original equation. Do you see now why we need it?
Yeah, is that always going to be like 0? Like
This part will always have an x plus 2 or something on the bottom and go to 0, and you'll have the equation of a line. And remember what I said, and this ties back to something, I think it was Adam that said this. If the difference between the degree of the numerator and the denominator are the same, how would this be different, right? Like you said, that's going to be a line. So how would it be different? You start to think about what that graph would look like. That was rhetorical. Or are you asking a question?
Yeah.
Oh, I thought you were going to answer that. Go ahead.
So, are you saying that the asymptote is equal to the function then?
No. But as I get out far away from the middle,
Oh,
basically.
okay.
But that's true of horizontal asymptotes too, isn't it?
Yeah, because it's
Yeah. And that's good. That's a way you want to think about it, though. Like when I get out there, it's basically that. Because this is negligible. It's nothing. It's 0. We're basically this line. What do we notice about this one? Okay, so it's degree 3 over degree 2. That's really important. Degree 3 over degree 2 means we're going to have a oblique asymptote. Well, no kidding, since that's what we're doing today. But anyway, we want to write that down. Like I think you want to make a note when you observe that. As opposed to a horizontal asymptote, right? Yes? I think probably. What else do you notice?
that we actually use one
Ooh, why do you say that?
because the numerator isn't at degree 1.
Yeah, the denominator, you mean the bottom isn't a degree 1, and that's what synthetic works for. I'm dividing by a degree 2, so I have to use long division. Good call. Anybody notice anything else?
Do you ever have to use the difference cubes?
Well, do we need to factor to sketch? Yeah, we need to factor. Remember I said always factor because that's how you're going to find your x-intercepts and your vertical asymptotes. We factor the top, we factor the bottom. If you're given factored form, you probably want to expand it. Unless it's going to be really messy or something like that. Maybe you don't. So we are definitely going to factor. It sure is. And remember we talked about this. Will this factor further? Check it with b squared minus 4ac. I think you'll find that it's negative, so this will not factor, and this is not solvable in the real number system. What the top being 0, what does that give me? When the top is 0? No. It's okay. No, that's the bottom. X-intercepts. So how many x-intercepts do I have? 1, because that has no solution, but that one does. So I have 1 x-intercept. Okay, and on the bottom, we're going to factor that too, because at the bottom is 0 are my vertical asymptotes. Huh? The top is the x-intercepts. If you go back and look at your work, I'm sure you were doing that. Where does the horizontal asymptotes comes from the coefficients? Yeah, you know that. And we have an oblique asymptote. We don't have a horizontal asymptote. Right? Okay, what do we usually start with? Our intercepts. How do I find my y-intercept? Set x equal to 0, so I've got 0 cubed minus 1 over 0 squared minus 2 times 0 minus 3. Negative 1 over 3, which is 1 over 3, which is 0.3. The decimals are useful. I mean, 1/3 is an easy one, but remember the decimals are useful for the actual graphing when you have to decide whether something is to the left or right of something else. If you put an x-intercept on the wrong side of an asymptote, you're going to really struggle when you go to try to draw that graph. Something is not going to work. Do we have any other y-intercepts? You better not. Do you ever have two y-intercepts? No, that would not be a function. Sorry, that was a trick question. Are you sure? Sorry, I hope I'm not confusing more than you already are. Sorry. You're never going to have, right? But think about that. You're never going to have, I don't want anybody to come up to the test and be like, ooh, are there any other y-intercepts? No. You only ever have one. You can have more than one x-intercept. What did we say our x-intercept was? 1? Because of that, right? I could have also solved this. Take the cube root of both sides. You can always just set the top equal to 0 and solve however you would solve. But if it's factored, that's how we usually solve, so you can just pick the x-intercepts out of there. Okay, so we've got one y-intercept, I hope, and one x-intercept. Asymptotes. We'll start with the vertical asymptotes. Does anybody care to help with what they are? X equals 3 and x equals -1. Very good, thank you. From when the denominator is equal to 0, because you can't divide by 0, so it's a vertical asymptote. There will never be a y value there. Think about what a vertical asymptote is. It's an absence of function. There will never be a y value in that entire x because you can't divide by 0. Horizontal asymptotes are different because you can cross them. It's just asking what happens when you go far out there. But vertical asymptotes are like, you cannot divide by 0. There's no way to make the function exist at that point. Okay, and well, let's do the testing of this first. I like to do it left to right. What are some good values to pick for this one? Remember, testing vertical is different from testing horizontal, which is also slightly different from testing and interpreting oblique. You got to know all the types. What are good values
2.999.
for -1?
No, for 3.
Okay, that would be good for 3. I started with -1. I flipped them because I was going left to right. Okay, good. I'm going to use that as my second one if you're okay with that. Because that's to the right. Do you agree? That's to the right? Yep. And the other one would be? Good. So I'm just to the left, then I'm just to the right. This one is a little bit trickier to me. I think you could use that to see if the top is positive or negative. And then maybe you could use that to see if the bottom is positive or negative. So what I mean by that is -1.001 all cubed will be negative. -1 is still negative, so the top is negative. And then -0.999 minus 3 is negative. 0.999 plus 1 is positive. So it's positive. Are we happy with that? Or maybe we should check it with our calculator. This mental stuff, think about that for a second. If you are hesitating and you're not sure, check it on your calculator. Negative 1.001. The top is definitely negative. That's negative and that's negative. I have 3 negatives. So the result should be negative. But sometimes it's tricky. Sometimes it's easier than other times. And then what about this one? Negative 0.999. So the top is still, what do you think? So the top, good. The top is still negative. But this part's negative, but that part's positive because negative 0.999 plus 1 will be positive. So you have 2 negatives, so it's positive.
Can I check with the negative 2?
Check with negative 2. What do you mean by that?
Because it's also on the left side of negative 1.
Yeah, I think that would work unless there's some reason, some number in between them that's changing it. You know what I mean? Like if 1.5 or something was in there, then you couldn't. But otherwise, yes, you could. Okay, so this one's positive. So that means as x approaches negative 1 from the left, y is going to negative infinity. As x approaches negative 1 from the right, y is going to positive infinity. X equals 3. So when we do our testing, we're going to find that this one works out to a negative and this one works out to a positive. You can always punch it into your calculator. 2.999 minus 3 is negative, plus 1 is positive, minus 1 is positive. So you got 1 negative, so it's going to be negative. And remember, they're not always different. They can be the same. They can both, from the left and the right, they can both be going positive or both be going negative. But in this case, they're different. Any questions about that? All right, now you're exactly right. Now we're doing the oblique. What's the first step of finding the oblique asymptote? Dividing. And remember what we already said, because we're dividing by degree 2, we have to use long division. I bet you hoped that you were finished with long division forever. Well, you are not. And what do I have to think of when I'm writing this out? Good job, ghost terms. This is minus 1. Okay, we'll do this quickly. X squared into x cubed goes x times. You don't have to just copy me. You can just do it. You guys know how to do this. X squared goes into 2x squared 2 times, so plus 2. And here's where we got to write out that funky part. We're going to shorten it this time. Last time we wrote down extra steps because we were kind of remembering what happened. So that's my division statement on top, both parts, and then separately divided by, and don't forget, what is this? This is the original denominator of the function, right? What we divided by. And those will always divide out because you design it to be that way. It's a little bit harder to see that this remainder is going to be 0, but this squared is going to be bigger than that line, right? Parabolas grow faster. Like squaring things is going to make the bottom grow faster than the top. So it is going to go to 0 for sure. So my oblique asymptote is y equals x plus 2, and my remainder is r at x equals 7x plus 5 over x squared minus 2x minus 3.
So can we always assume that second part will always go to 0?
Yeah. But if for some reason you did it and like you didn't have a bigger degree on the bottom, I would be wondering what went wrong. Oblique asymptote testing. Again, take a look. When I put negative 1,000 in here, what is the top looking like? Thank you. Negative 7,000 plus 5 is probably still negative. And then this is going to be positive because I'm squaring it. Negative 2 times negative 1,000 is positive. Those are both pretty big, so subtracting 3 is probably not going to make it negative. So the bottom will be positive. So I've got a negative over a positive. So this one is. Therefore, we are below. Now remember, you cannot do this with horizontal. What people do is they do the same thing with horizontal asymptotes. That does not work. Horizontal asymptotes, you need the value to compare to the asymptote to see if you're above or below. But because all we're doing is the remainder part, if it's negative, you're subtracting, so you're below. And if it's positive, you're adding, so you're above. Whoops, I wrote that in the wrong spot. Is that what you were going to tell me, Seema? Thanks for looking out for me. Okay, so then 1,000 goes here on top, and I get positive. And I get a big positive minus a smaller negative. So that's negative 2,000. That's not going to be big enough. What's 1,000 squared? That's pretty big, right? Minus 2,000 is still positive. Minus 3 is still positive. So I've got positive over positive. Therefore above. What's harder, that part or the sketching part? Both, yeah. The sketching part, I bet you some people find one, some people find the other. I would wonder, but I would agree probably a lot of people think the sketching part. So I'm going to draw in my asymptotes and my x-intercepts. I've got a vertical asymptote at x equals negative 1. I happen to know a little bit what this graph is going to look like, so I'm keeping it kind of like tight distance there. And x equals 3. and I've got a y-intercept of 0.3 and an x-intercept of 1. So I'm going to start labeling these. I should have labeled them as I went. My oblique asymptote is x plus 2. So it has a slope of 1 and a y-intercept of positive 2 and an x-intercept of negative 2. Something like that. If you graph this line wrong, and this point that my oblique asymptote is going to go through was on the wrong side of the asymptote, it is not going to work. So you got to make sure you get that line right. I think that's it for asymptotes. We happy with that? Yeah.
Oh wait, that's just for the asymptote. So we're gonna actually graph, or we're gonna sketch.
Yeah. So we're going to do behavior on the asymptote. So here's my -1 asymptote. When I approach from the left, I'm going down. When I approach from the right, I'm going up. So that's this one. When I approach from the left, I'm going down. When I approach from the right, I'm going up. Next asymptote at 3. When I approach from the left, I'm going down. When I approach from the right, I'm going up. Oblique asymptote. When I'm going off to the left, I'm going below. When I'm going off to the right, I'm coming from above. So below looks like this, and above looks like this. If you want to put your pencil down and watch, you can do that. What does this look like? It looks like this. Look at this one. Everything fits, right? Is this go all the way up through the x-axis and back down? What do you think? Maybe? Maybe? No? Don't think so? Why not? Does this part here come all the way up here into the corner through the x-axis? How do we know? There's no x-intercepts there. So we don't know exactly what it does, but it's going to go like this. Try to make it a smooth curve. And now remember what we said, how our function, the blue part is our function. But when I get way out here, it basically looks like that line. Remember when we said that? So see how that's true? It's basically going to be this line forever now. And when I get up here, in here it doesn't look anything like the line. But over there, it does, because it goes way off there. Make sure everything is labeled. Any questions?